Another point to note will be the bond angles between the bonds. We started off with tetrahedral molecular geometry, where we get 109.5 degrees between the bonds. As we replace the bonds with lone pairs, the bond angle will become smaller and smaller. Right? This is because the lone pairs will require a larger space. There will be more repulsion, so the bond pairs are forced to move further away from the region. So trigonal pyramidal will have a smaller bond angle than tetrahedral. A band where there are two lone pairs, the bond angle will be even smaller, right? Because now you have two massive lone pairs occupying the region, and the repulsion will push the bond pairs away from the region. So the angles will become smaller as we add more lone pairs rather. So this is for 4 electron groups. Let's look at 5 electron groups. Again, the simplest one to start off with will be remembering when all of them are bond pairs. So 5 bond pairs, 0 lone pairs, we have this shape. There are two main areas to look at. First of all, there will be two parts that is vertically opposite each other, or they form a linear line. These are what we call the axial position. It's like the north pole and the south pole axis of the Earth, right? This will be the axial position, and there will be 3 other groups that are what we call lying in the equatorial position. It's like the equator of the Earth. So the angles among them, from the axial to the equatorial, they will be 90 degrees, right angle. But the equatorial positions, if you look from the top, is 300 degrees divided by 3 groups, so 120 degrees each. The shape, we can visualize that there are actually 2 pyramids. The first pyramid, imagine this to be the tip of the pyramid, and then is joined to the three molecules or 3 atoms. It will form a pyramid with a triangle base. We can also form a pyramid from the bottom. From this end, it will join to the 3 atoms. We have another pyramid that has a triangular base. So there are 2 pyramids with triangular base. That's why I call it trigonal bipyramidal. Remember just now we have a pyramid with one pyramid with a triangle base. We call it trigonal pyramidal. Right, now we have 2 pyramids with triangle base. We call it bipyramidal. Now we will start replacing the bond pairs with lone pairs. 4 bond pairs, 1 lone pair. Here it is important for you to know where we will place the lone pair. We can't replace anyone that we like. We will find a region where there is the most space for the lone pair to exist. That region is on the equatorial bonds. We will be replacing the equatorial bonds rather than the axis bonds. Because the axis bonds, it is 90 degrees to 3 other groups of electrons. Whereas for the equatorial ones, you have a much larger space to exist. So we will replace the bond pairs at the equatorial position, and then we end up with this shape. It takes a bit of visualization, but you can try to see that it looks like a seesaw, right? These are the pivots, and then these are the two ends of the seesaw. So that's the molecular geometry, which we don't take into account the shape of the electron, the lone pair here. Some books you might see being called a distorted tetrahedral. So that's 4 bond pairs and 1 lone pair. What happens if we replace another bond pair with a lone pair? This time again we'll be choosing a bond pair from the equatorial position. The molecule will look like this. The axis position will not be replaced. So now we have 3 bond pairs, 2 lone pairs, total of 5 electron groups still. So it's still under this particular electron geometry. So electron geometry, no change, is trigonal bipyramidal. Molecular geometry will just focus on the bonds again. It will be T shape, right? It looks like an alphabet T on its side, or rather it looks like the letter T on its side. Right. Although we call it T shape, just keep in mind that it is not totally or not exactly 90 degrees between these bonds, because the lone pairs, due to their repulsion, will actually push these 2 strands or these 2 bonds to the left. So you will be expected to be slightly less than 90 degrees. Next one, what happens if we replace one more bond pair? We end up with 2 bond pairs and 3 lone pairs. Again, the equatorial bond pair will be replaced. We have this shape. All the equatorial positions are replaced. We only have these 2 bond pairs left. And ignoring all the lone pairs, we can see that the molecular geometry is simply linear, 180 degrees. Right, so remember the trigonal bipyramidal shape, and then start to replace your equatorial positions with lone pairs. Then you will know the shapes that the molecule will have.